Okay, hi everyone, and welcome to this third lecture on quantitative spectroscopy of massive stars. So today with Evgeniia, we're gonna determine stellar and wind parameters. So we have a bunch of stuff to go through here. So let me introduce a little bit the speaker first. So Evgeniia is in her final year PhD, working at as a research fellow and senior lecturer already at Kazan Federal University. She did her PhD and master studies at the same place. She is studying hot X-ray emitting stars based on integral and spectrum Röntgen gamma observations. And she will graduate somehow late 2026 or early 2027. And I would like to take the opportunity that we have her today to advertise one of her latest paper that was in Astronomy Letters published in 2025, which is about the study of massive OBE stars with X-ray emissions. So if you are interested, and I'm sure you are, I can only recommend you to go and to have a look at her publications. So, okay, so Evgenia, if you're ready, then the floor is yours.
Sophie, thank you for your introduction. And first of all, I would like to thank the organizers for creating this lecture course of massive stars. It has been a very valuable experience, not only for learning new material, but also for presenting it and interacting with experts in this field. I would also say thanks to these experts, Frank Banks and Gonzalo Olgada, for their guidance, insightful comments, and help in preparing this lecture. Let me briefly outline today's talk. I will start with a short introduction, then discuss the fundamental stellar parameters, followed by line broadening effects and stellar wind parameters. At the end, I will briefly mention two important open questions: discrepancy problem, the mass discrepancy problem, and the stability jump. And I finished with a short summary. So let's begin with a general introduction to the topic. And I want the slide show a quick overview at what we are dealing with. A stellar atmosphere is a thin outer layer where no energy is generated, only redistributed, and where the emergent spectrum, including both continuum and lines, is formed. We already learned from Gonzalo Oldaga's lecture how spectra are obtained observationally, and Carlos Martinez Sebastian discussed the synthetic atmospheric coders used to compute theoretical spectra. What I will focus on today is quantitative stellar spectroscopy, how we compare observed spectra with model atmospheres and derive effective temperature, surface gravity, wind parameters, and other parameters of stars. And for chemical composition and abundances analysis, Alba Casabuenas will discuss in 2 weeks. Determining stellar parameters is not a simple step-by-step process because different physical parameters affect the same spectral features at the same time. This slide shows one example of an analysis strategy. The main point is that stellar parameters determination is a strongly coupled problem. Temperature, gravity, abundances, and wind properties all influence the spectrum simultaneously. Because of these parameters cannot be derived independently. Instead, we use a combined and iterative approach, where several diagnostics are fitted together in a self-consistent way. The scheme shown here is just one example of how such an algorithm can be organized in practice. In general, different analysis methods may follow similar iterative workflows, but with variations in the choice of diagnostics and optimization strategies. Before discussing individual parameters, it is important to understand why different wavelength regions are used in stellar spectroscopy. The accessible diagnostics depend on both ionization balance and the spectral energy distribution. Hot OB star emit most of their energy in the ultraviolet. So the ultraviolet is especially important for studying stellar winds and intrinsic stellar properties. The optical range, we used the classical diagnostics of stellar atmosphere analysis, helium and silicon ionization balances, together with hydrogen Balmer lines. This provide the main constraints on effective temperature and surface gravity. In the infrared, extinction is much weaker, which allows us to study heavily reddened or embedded objects. Here, hydrogen recombination lines such as Paschen and bracket series become important diagnostics. With the general picture of mind, we can now move to the determination of the fundamental stellar parameters, and we begin with the effective temperature, since it strongly shapes the overall appearance of the spectrum. The first step in spectroscopic temperature determination is the ionization balance. If we compare two spectral lines coming from consecutive ionization stage of the same elements, their intensity ratio becomes very sensitive to temperature. This is why ionization balance works as a stellar thermometer. Here we see the Saha equation, which gives the ratio between the population of two ionization stages. The ratio depends exponentially on temperature and more weakly on electron density. However, in real spectra, we do not observe ion population density directly. We observe spectral lines, and their strengths also depend on how many atoms are in the excited states responsible for these transitions. This is where the Boltzmann equation becomes important. So we move from ionization to excitation. The Boltzmann equation describes the population ratio between different energy levels inside the same ion or atom. The arrows in the hydrogen diagram represent radiative transitions, downward transitions from excited state that produce the spectral lines we observe. The line intensity is proportional to the upper level population multiplied by Einstein coefficient. The temperature affects both the ionization balance and the excitation balance, and together this determines the observed line strength. By combining ionization and excitation, we obtain the final temperature diagnostics for line. The ratio of two spectral lines be different lines from different ionization stage constrain both the Saha term and Boltzmann term. In practice, we measure this ratio, we can directly estimate the temperature of stellar atmosphere. And this is basic principle behind spectroscopic temperature determination. Now, let us look at a particular example for R-type stars. For R-star, the classical temperature diagnostics is the helium ionization balance, especially between helium-1 and helium-2 lines, helium-1 4471 and helium-2 4542. We see how with temperature increasing helium-2 lines and decreasing helium-1 lines. For B stars, helium becomes less reliable as temperature diagnostics, especially when helium is mostly neutral. In this regime, silicon ionization balance becomes the main temperature indicator. As temperature increases, the dominant ionization stage shifts from silicon 2 to silicon 3 and then to silicon 4. So the same physical principle applies here as well. Increasing temperature shifts the ionization equilibrium towards high ionization stages. And we can see how decreasing silicon 2 lines and increases silicon 3 and silicon 4 with temperature. This slide shows a more quantitative view of temperature diagnostics using equivalent width. Here we can see how the equivalent widths of different lines vary systematically with effective temperature. I already discussed about helium in silicon, and now I want to say about nitrogen. Here we can see how changes balance between nitrogen 4 and nitrogen 5. In the ultraviolet range, determine the effective temperature becomes more challenging because the spectra are dominated by dense metal, especially from iron. This iron line forest mainly consists of iron 4, 5, and 6 transitions. As we can see in the the dominant ionization stage changes with temperature. This again reflects the ionization balance. Because of strong blending, these features are not used as simple line ratios. Instead, the observed spectra are compared directly with models, and the iron forests provide an additional temperature constraints. This becomes especially important for very hot stars where many important diagnostics are located in the ultraviolet. In the near-infrared, helium ionization balance work again, and we can use here these lines. Helium 1, 2.056, strongly affected by line blanketing and wind effects. And helium 1, 2.112 microns preferred for diagnostic because, this line weaker, but more reliable. We have only one line in helium 2 transition is 2.189 micrometers, and this line located in K-band. And this again worked ionization balance method. After temperature, we now move to surface gravity and hydrogen line broadening. In a stellar atmosphere, hydrogen atoms are surrounded by electrons and ions that create local electric fields. These fields perturb the atom and produce the Stark effect, which broadens and shifted the hydrogen energy levels. The Stark effect mainly affects the winds of the hydrogen lines. The line core form in higher, lower density layers, where Doppler broadening and radiative transfer dominate. In contrast, the wind form deeper at the atmosphere, where electron densities are much higher and Stark broadening becomes much stronger. The strength of this broadening depends directly on electron density. More electrons produce stronger local electric microfields and therefore broader wings. Since higher surface gravity corresponds to higher pressure and electron density, the Balmer wings become a very sensitive diagnostic of log G. This slide summarizes the main gravity diagnostics in both the optical and near-infrared. In the optical, surface gravity is derived mainly from the wings of Balmer lines, which are strongly affected by Stark broadening, but H-alpha is often significantly contaminated by stellar winds. In the infrared, the alternative is to the bracket lines, and in the figure shows how the profiles vary with increasing log G as fixed temperature is around 225 kilokelvin. So far, we discussed temperature and gravity separately, but in real spectral fitting, they are determined simultaneously. This introduces an important degeneracy between effective temperature and surface gravity. Barrier winds mainly constrained gravity through star broadening, while ionization balances constrained temperature. However, similar spectral changes can sometimes be reproduced by compensative variations of both parameters. For example, increasing temperature weakens Palmer lines, while increasing gravity broadens them. As a result, effective temperature in log G becomes correlated, producing the elongated error ellipse shown in the figure. This is not a limitation of the method, but a physical degeneracy of the spectra themselves. Using multiple diagnostics and high-quality data helps reduce this effect. Now we move to another fundamental stellar parameter is bolometric luminosity. Traditionally, luminosity was derived from optical or near-infrared photometry using bolometric correlations. In this approach, we start from the absolute magnitude and apply bolometric corrections that depends on effective temperature. A closely related method is synthetic photometry, where observed magnitudes are compared directly with theoretical magnitudes obtained by convolving a model spectra with filter response function. Nowadays, the standard approach is spectral energy distribution fitting. Here, spectrophotometry from the far ultraviolet to the infrared is fitted with model atmospheres, allowing us to determine the global flux scale directly. At the same time, the reddening AB minus V can be derived. In addition, any excess emission, for example, due to dust or circumstellar material, can be identified and modeled separately. An example of the set you can see here on the figure. And that's all about fundamental parameters. Those parameters define the physical state of the atmospheres and overall spectral energy distribution. However, to reproduce the detailed shapes of spectral lines, we also need line broadening parameters. Spectral lines are broadened by several physical broadening processes, including thermal and pressure broadening, stellar rotation, and turbulence. Among these two particularly important parameters are the projected rotational velocity within I and macroturbulence, which strongly affect the detailed line profiles. We now focused on how stellar rotation is measured from spectral line profiles. In O and B stars, line shapes are mainly controlled by two broadening mechanisms, rotation and microturbulence. Rotation produces Doppler broadening across the stellar disk, while microturbulence is associated with large-scale velocity fields in the atmosphere. Here we can see how macrolimbs influence on shape of lines. Also, both broadened the lines, their signatures are more identical, which makes the separation non-trivial. To measure the projected rotation velocity within I, we usually use isolated photospheric metal lines, and we can obtain the value of projected velocity using Fourier transform method. In Fourier space, rotationally broadened profile has a characteristic first zero whose position directly constrains V sin I. In practice, rotation and microturbulence are strongly generated in spectral fitting. To separate them, we use a grid-based goodness of fit approach. Synthetic spectra are computed by convolving intrinsic profile with rotational and microturbulent broadening, and a chi-squared minimization is then performed. An important point is that the Fourier transform method provides an independent constraint on V sin I because is the relatively intensitive to macroturbulence. By comparing both methods, we can break the degeneracy and obtain a physical consistent solution. The chi-square map shown here illustrated this clarify different combination of V sin I and V mark produced a long elongated value, while the two constraints select the correct solution here. Up to this point, we mainly focused on photospheric properties such as temperature, gravity, luminosity, and line broadening. However, massive stars lose mass through powerful stellar wind, which produce additional spectral features beyond the photosphere. So now we move to the second part of the talk, stellar wind diagnostics. And let us start with one of the main wind parameters, the terminal velocity. It is simplify the maximum speed reached by the stellar wind far from the star, where the acceleration effectively stops. Observationally, this is measured from using P-sigma profiles. These profiles consist of blue-shifted absorption and redshift peak. The absorption is produced by wind material on the near side of the star moving toward us, while the emission comes from material on the far side scattering photons into outline of sight. The combination of blue absorption and red emission is the characteristic signature of an expanding stellar wind. From the extent of the blue absorption, we can estimate the terminal velocity. And there are two methods for this, direct methods. For strong saturated profiles like this on the bottom, we can measure the terminal velocity using VH velocity. A better approximation is black absorption H, the bluest velocity, where the residual flux reaches zero. For unsaturated profiles like this, we can use additional method. Unsaturated profiles are narrow absorption components. These components you can see here, and these are discrete absorption features that migrate through the profile towards higher velocities. In practice, this requires time series ultraviolet spectroscopy to track their motion, which makes the method expensive. And modern method for determination of terminal velocity is Sobolev with exact integration method. In this approach, the wind velocity field and opacity distribution are parameterized, and synthetic P-sigma profiles are fitted directly to the observations. The method simultaneously constrained the terminal velocity, turbulent velocity, and wind opacity structure. An important advantage of CEI method is that it accounts for turbulent broadening. In turbulence is ignored, the blue absorption edge becomes artificially extended, leading to an estimate of V infinity. The figure on the right shows an example of CEI fitting for the resonance doublet of carbon. Sometimes ultraviolet spectroscopy is not available. In this case, the terminal velocity can be estimated using empirical scaling relationship from radiation driving wind theory. A key parameter here is the escape velocity. This is the minimum velocity required for material to escape the stellar gravitational field. Within this theory, the terminal velocity scales with the escape velocity, and the line-Braun parameters connection this equation. In practice, a simple approximation comes from the stability behavior of stellar winds. For hot Earth stars with temperature greater than 25,000 Kelvin, we typically find V infinity between 1.3 and 1.5, between 2.5 and 3. But for cooler, it's about 1.5, 1.3. This slide summarizes the main diagnostic used to determine terminal velocity. Different wavelength regions probe different wind regimes and physical conditions. In the ultraviolet resonance line to provide the most direct and sensitive diagnostics, especially for strong winds. And the optical hydrogen and helium lines can also be used, especially for a late evolutionary star. In practice, several diagnostics are usually combined to obtain a robust estimate of V infinity. We now move to another key diagnostic parameters. This is m dot. There are two classes of spectroscopic diagnostics here. This is P-Cygni profile in ultraviolet, P-Cygni resonance lines in ultraviolet, and H-alpha light, of course, in optics. And in both, we use the same important relationship between dot m and rho. Dot m is divided by r squared times V infinity. So if we can estimate the wind density from spectral lines, and if the stellar radius and terminal velocity are known, we can derive dot m. UV resonance lines depend linearly on dense and are therefore extremely sensitive. This is give us opportunity to measure m dot for lower values like this. H alpha, on the other hand, is a recombination line and scales of rho squared. This makes it less sensitive to weak winds, but also less affected by ionization uncertainties, since hydrogen is almost fully ionized in all-star winds. In practice, ultraviolet diagnostics are mainly used for weak winds, while H alpha is more useful for stronger winds. This slide focused on UV resonance lines, which are among the most sensitive in diagnostics. The transitions shown the trace different ionization stages in the stellar winds. The figure on the right shown an example of fitting Picigny profiles to constrain m dot. However, an important complication is wind clumping. Stellar wind are not smooth, but contains dense inhomogeneities. This is described by the volume filling factor, which measured how much of the wind volume is occupied by dense material. Typically, filling factor decreases from values close to unity near the sonic point to a smaller asymptotic value in the outer wind. Clumping affects both the ionization structure and the derived mass loss rate, especially for diagnostic proportional to rho square, such as H alpha. If clumping is ignored, the derived mass loss rate can be significantly overestimated. One advantage of H alpha line is that it is relatively insensitive to ionization effects, since hydrogen is almost fully ionized in all-star winds. The main limitation is sensitivity. For mass loss rates below about 10 in -8, H alpha no longer shows the wind emission and becomes purely photospheric absorption. In this regime, the wind signature essentially disappears. An additional optical diagnostics is helium-246-86 line, which can also form in the wind and provide complementary constraints. This table summarizes the main wind diagnostics across different wavelength ranges. Rather than focusing on individual transition, the important point is how differently the diagnostics responds to wind density and ionization. UV response lines depend roughly on m dot and the ionization fraction, while recombination lines depend on m dot in square. Optical hydrogen lines, especially binary lines, are also useful in some classes of massive stars, including Wolf-Rayet stars. This slide summarizes the main methods used to determine mass loss rates. All of them are based on this relationship. The last wind parameters we discuss is beta, which describes how the wind accelerates from the photosphere to the terminal velocity. The standard velocity law is given by this expression. Typical values we can see here for all-star and supergiant. And on the right, you can see fit of H alpha life for different values of beta. Green for beta equal 0.5 and red for beta equals 1. And in the end of my talk, I want to say about two open questions. Mass discrepancy is the first of this, and this refers to the systematic difference between spectroscopic and evolutionary masses. The spectroscopic mass is derived from log G and radius. Radius we can obtain using luminosity and temperature. And evolutionary mass obtained by comparing the position of the star in the HR diagram with the stellar evolution tracks. As shown in the figure, we can see that evolutionary masses are often systematically larger than spectroscopic masses. This problem has been known since the 90s and is still not fully resolved. And the second open problem is the stability jump. Theory predicts that when all stars cool below about 25 kilkelvin, iron recombination from 4 to iron 3 changes the wind driving. This should produce a drop in V infinity by about a factor of 2 and an increase in m dot by roughly a factor of 2.7, while keeping V infinity approximately constant. This behavior is included in many stellar evolution models. However, observation only clearly confirm the decrease of terminal velocity. The predicted increase in mass loss rate is generally not observed. This suggested that the stability jump is still not fully understood and that current wind prescription in the temperature range are probably inaccurate. Overall, observations remain essential for testing and improving theoretical models of massive stars. And finally, I want to give a short summary using great infographic collects from Ulysses project for O-star and for P-star. It provides a very nice overview of the diagnostic discussed through this talk. And thank you for your attention.
Thank you very much, Evgeniia, for this great overview about everything that we can derive from the spectra. It was extremely, extremely nice. Do we have question in the audience? I have plenty, but I would like the audience to ask their question first. No. Okay, so let me.
Okay. Yeah, I have comments as usual, since this is at the heart of my science. So let's show pulse here. Can I give them, or do you want to have somebody else?
No, you can go. I can ask my question later.
Okay,
Go for
good.
it.
So this was a really nice overview about more or less everything you need to know when you are doing quantitative spectroscopy, and I have only a few comments, but nevertheless they might be important since this thing will go, of course, also on the internet, and then one might need some additional comments. The first comment is regarding the scaling of the terminal velocity. You have provided the standard equation for the escape velocity, which is completely correct. However, the scaling relation, which was derived by Castor, Abbott, and Klein for the first time, is not referring to this classical escape velocity, but to a slightly modified escape velocity, namely below the square root, there is a 1 minus gamma, where gamma is the Eddington factor. So when we are close to the Eddington limit, then the escape velocity in this way, this modified one, is smaller than the classical escape velocity, and therefore this has a big effect also on the terminal velocity. This is number one. But moreover, nowadays, since we have much more experience with this old empirical scaling equation is more and more often replaced by findings and scalings from Callum Hawcroft et al. Namely, he found that for a large range of stellar parameters, there is a very nice relation of V infinity on the effective temperature alone. And the problem when we usually when we had the former relations as a function of the escape velocity was always that one needs to know the stellar radius, which is sort of difficult. But with this new relation by Hawcroft, this problem is no longer there. So that was my first comment. And the second comment refers to the mass loss determination from ultraviolet lines. I just want to add something which also needs to be accounted for, namely, in addition to saturation effects, which makes it difficult to use the ultraviolet for very strong lines, for saturated lines, and so high mass loss rates are difficult from the ultraviolet. There's another problem, namely that all these lines, or most of these lines, as you have written here, for the phosphorus 5 line, are strongly affected or might be strongly affected by X-rays. So when you go through all the lines, and it turns out that actually mostly only the carbon 4 line is almost free from these effects. So when you want to analyze mass loss rates, you should concentrate on carbon 4 and those conditions where it is not saturated. So this is what I wanted to add. Thanks a lot once more.
Thanks a lot, Joe, for your comments. Does anyone wants to react or ask a question or make another comment? Okay, then I will take my privilege and ask a question about your, well, it's not really a question, but about your slide 37 when you present the B-stability jump, the problem of the B-stability jump. It seems that this has been, so it's 37, sorry.
37.
Yeah. So it seems that this B-stability jump has been solved, for instance, if you look at the massless rates that are predicted by Björklund 2000, there are several papers, 2020 something. And also in Krichka papers, this B-stability jump is still present, but it's weaker than the one from Vink. So can you maybe comment on that and explain what happens in the models or?
Thank you for your questions. And I use information from this paper, Burgos and al. 2024. And here the authors give this picture, and they says that we didn't have, observationally, we didn't have the stability jump here. And we can't argue with observation. Observation gives now this information. And I think theory have to explain the observation.
Yeah, that was exactly my question. Is now that Vincatel dates back to 2001, but there are new prescription nowadays, Björklund, Krichka, that can be debated, but that do not show this. So but okay, maybe Artemio, you raise your hand, so maybe you want to comment on that, or?
Thanks. No, actually, I only wanted to comment on the determination of the radius.
Okay.
By the way, that was a very nice talk, really well structured and very clear. Simply to comment, as Joe said, because we are in the internet, that it's better to determine the radius from the magnitude of the star, from the absolute magnitude and the extinction of the star, rather than from directly from the luminosity and the temperature. It's more accurate, simply.
Yeah.
So, Sophie,
yes,
if I would comment on the B-stability jump that you were saying, and well, really nice talk, Evgeniia.
Thank you.
Yeah, the new prescriptions could be more related to these observational results, but we know that there are some people observing and finding that hypergiants do appear on the other side with higher winds. So maybe they were observed before because they were more luminous, and that's the reason why at the beginning they decide to find this B-stability jump. I mean, to introduce this iron change to understand. So with more observations, maybe we will find that there is a still need for something there for the hypergiants. So something is happening there, but not for all of them. So yeah.
Thank you. Joe, yes.
Yeah, I'm not Gonzalo. In this case, I'm not completely agreeing with you. The reasons that the B-stability jump actually was introduced was, as you said, more or less pinned or confirmed by observations, but in this case not on the mass loss rates, but on the terminal velocities, which of course also are much more easily to determine than the differences in mass loss rates. So this is a very nice paper by Henny Lammers and colleagues, where he showed that just at this B-stability jump, the terminal velocities are decreasing significantly. But from the beginning on, there was always a problem with the mass loss rates. In the former times, the mass loss rates were quite difficult to determine. And so the Yorick-Finks argumentation was always still, or in my opinion, it is still valid, namely that when you decrease the ionization fraction, ionization ratios from iron 4 to iron 3, then because iron 3 has much more lines than iron 4, you should increase the mass loss rates. So the counter argument by Björklund in this case was that indeed, particularly in the typical B supergiant domain, I'm not speaking about B hypergiants, but B supergiants, that in this domain, it might be that iron is not as important for the total line acceleration as standard-wise argued, and therefore this increase in line number does not play such a big role. So I mean, it's somewhat difficult to understand why you do not get this kind of stability as a prescription. But in any case, it seems that both the observations as well as the newest hydrodynamic models do no longer show this increase in mass loss rates, but only the effect on the terminal velocity. So please keep in mind that the measuring was always related to the terminal velocity.
Okay, thank you, Joe.
Thank you, Joe. I see question in the chat, so maybe I can ask them. So someone is asking about how to determine alpha in the empiric relationship between escape velocity and terminal velocity. So Evgeniia, can you maybe show us back that relationship between between escape velocity and terminal velocity, and tell us about how to derive alpha for.
I think this is the parameter from theory, because this equation from this theory, Castor-Ebert-Klein.
Yeah, but which value of alpha do you get?
I can't hear right now to say which equal I see. I would to see this paper. I think you can see this parameter in here.
Yeah, the standard value of alpha is on the order of 0.6, but for A-type supergiants, it can go to 0.4. So when you take the average value of 0.5, then you have just for this factor a unity there. So this tells you that the terminal velocity should be on the order of 2.2 times the escape velocity. And that's the best you can do. Indeed, you almost cannot measure it unless you would really believe in this kind of CAK theory, which has also some drawbacks, and therefore, as Evgeniia said, this is a purely theoretical value and results as a byproduct, by the way. So when you are doing this kind of spectroscopic analysis, you always use these model atmosphere codes, and these model atmosphere codes have to use big line lists. So when you plot the line lists or the strength of the line as the number of lines as a function of their strength, then from the slope you can actually get this alpha parameter. There is quite a literature on this, but all this is theoretical.
Thank you, Joe. So I hope that answered the question in the chat. I have another question in the chat. Yes, it answered the question. So I have another question. So it's more a commoner question, not sure, but it is about determining the beta parameter from spectra, especially for cooler supergiant where dust may be primarily driving the wind. So not if the person who asked the common question wants to speak up to clarify, maybe if it's not clear.
This is difficult because I mean, dust driving is only for the very cool stars, and the very cool stars are no longer line driven. So whether they have a better velocity or some other velocity law is a different question. They have, I mean, these are the red supergiants, which have term velocities on the order of very few sound speeds. So, and from all the OBA stars or even LBVs, I do not know, or I have never heard that dust driving in the outer part should be some important acceleration mechanism. So maybe the guy, whoever asked this
Actually,
question,
yeah,
yeah,
actually, I wanted to just comment that we are working on similar lines to
ah,
investigate the role of dust in driving the wind, but
yeah, but
from
for which stars? This was the
mostly
question.
for red supergiants,
Yeah,
yeah.
okay, good, yeah.
So, but I wanted to say that the beta parameter is quite like it's very sensitive to what we infer about, for example, post-explosion observations and how we infer many parameters from the post-explosion observations of the stars. And
But
we
how
have
do you
studied that systematically in this paper I referenced. So,
how do you come to the idea that in these kinds of hypothetically dust-driven winds, and they might be also driven by other processes,
mhm.
that you have there still a better velocity law? I have
No,
no
no, no.
idea.
There is no evidence or there is
Yeah,
no theory
yeah,
for it.
yeah.
People use it as a
Okay.
extension of the hot star winds to the
Okay,
to,
good. So
yeah.
that's
So
completely new to me. I would never do
yeah,
this.
yeah. But it has been done over more
Okay.
than a decade to
Oh, okay. Interesting.
explain post-explosion observations.
That's interesting. So maybe the people who have done this should look into the literature.
Okay, so I think that we can say that it answered the comment. Do we have any other question? Because I have one more otherwise. I think I will go for it. So, you said that from the P-Cygni profile in the UV, but also from H alpha in the optical, you can derive um, the terminal velocity, and you can also derive the mass loss rate. But how do you do, for instance, if you only have the optical, you have one line and you have to derive those two parameters on the same line? What what do you do when and how do you disentangle the effects of the velocity and the mass loss rate?
It was a very long question.
Okay, so you have the H alpha line, and so you have your spectrum in the optical, you have the H alpha line. How do you disentangle between the terminal velocity and the mass loss rate? Because both are derived on the same line.
Yes, it's complicated, and I I say about in the beginning of my talk, and here we can that for one line we have different processes, and for H alpha line we usually use this for dot and clumping together, and for different lines we sometimes have to use together these effects, and we can separate it. And
I mean, I guess what Sophie was asking for is what are you doing then with the terminal velocity? And the answer is very simple, namely for these kinds of, when we have only optical observations, then we cannot test on the terminal velocity, except that the H alpha line has a very strong emission, so that the emission goes until the terminal velocity. In this case, you would have a measurement. Otherwise, you're using just these kind of scaling relations which were mentioned. So either the scaling with the escape velocity or the scaling with the effective temperature, and the rest goes into the error budget.
Thank you. Do we have any other questions, comments? No, I don't see anything anymore. So maybe we can thank the speaker again, and we meet in 2 weeks for the next talk.
Okay.
Very nice. Okay.